Welcome to the Building Science Podcast.
Welcome to this. Okay. Welcome to the
Building Science
Building Science
Podcast.
Welcome to the Building Science Podcast.
Bringing the human factor to architecture and design.
Brought to you by Positive Energy in Austin, Texas.
Okay, hello and welcome back, everybody. Welcome back to the Building Science Podcast. I'm Kristof here with my trusty sidekick.
Hello, everybody.
Do you feel demeaned when I say sidekick?
No, it's because I'm kicking you in the side.
We're absolute peers, side by side, shoulder to shoulder. Oh, kicking me in the side. Good. I'm also here today with Chris Smith with Zehnder. Say hello, Chris.
Hello, Chris. No, hi. Hello, Building Science Podcast listeners.
And let's go ahead. Let's switch around. Let's start with your introduction. How did you come to do what you do? And what do you do?
Yeah, I'm currently business development manager for Zehnder America. Zehnder is a Swiss-based company that's interested in indoor climate concerns. It's got a global presence. Here in the U.S., Zehnder America focuses primarily on residential ventilation. And coming to our business, it's been around for about 8 years now. But
the residential side has been around for about 8 years.
Zehnder America.
Zehnder
so
America.
The American division that is focusing on residential ventilation.
Got it.
Yeah, but they're basically Zehnder America markets products that have been in use through the Zehnder group in Europe for quite a while.
Awesome.
Yeah.
Okay, I'm gonna start there with my introduction, then we'll get back to the interview. So ventilation, that word ventilation, it's interesting how something so simple can be so still not well understood in our so-called modern advanced building community. And so those of you listening, chances are good that two things are happening. One is that you're breathing, and two is that you're in air somewhere. Even if the air is coming out, I guess, out of a scuba tank, you're still breathing, and that air came from somewhere. But it's so common that we breathe and that we are immersed in air that we lose track of it. To say that air is just, it's just oxygen and nitrogen and some trace gases, that's like saying water is just hydrogen and oxygen, right? There's this oversimplification of the fact that breathing clean air is important, such that we almost don't pay attention to it. Very much like breathing clean water, right? So I used to...
or drinking.
Or drinking,
better.
Excuse me. We don't breathe clean water. Maybe you could edit that. So I used to work at a marina. I was a mechanic on boat engines. And my God, the water in the corner of the dock on a hot summer day, that was not
foul.
Clean water. And so...
But it's mostly hydrogen and oxygen.
But it is,
Yeah.
exactly. So it's if it were air, right? Unfortunately, a lot of the pollutants we're exposed to in air in indoor environments, the particles and the gases, our bodies and our neocortices don't detect them. They don't say, warning, this is not good air to breathe, and what would you do anyway? That's maybe a roundabout way of just trying to underscore this very basic and yet profound importance of breathing clean air when we're inside.
Yeah.
Okay, for those of you listening, we're not going to go through all the different types of ventilation systems right now. At least that's not my intention. My intention is to talk about the best ones. Just to frame this discussion, we want to get through this in about an hour, 40 minutes to an hour, and if we don't get to the good part, I don't think we'll make that. And by good part, I mean where ventilation systems really need to go, where they already have gone, but as far as technology, but as far as awareness and will and the skill to integrate it hasn't gone. So just for completeness, there are exhaust-only ventilation systems. They are very commonly done. There are supply-only ventilation systems. They are very commonly done. And then there are appropriate ventilation systems, which are balanced, mixed, and here's the big word, tempered. Could I get turned to you, Chris? Could you describe tempered?
I think tempered is a good way. All three of those basic types of ventilation systems that you just mentioned have the effect of moving air, changing indoor air with outdoor air. Mm-hmm. For much of the year and almost every climate, the outdoor air may not be exactly what you want to live in.
Mm-hmm.
as you exchange that air, ideally what you want to be able to do is probably filter it
Yeah, definitely.
and condition it.
Mm-hmm.
You can condition it.
By that you mean changing the temperature.
Yeah,
and
change
humidity.
the temperature and humidity. There are costly and energy-intensive ways of doing that, and then there are less costly and less energy-intensive ways of doing it.
There you go. Yeah. Okay, to narrow our focus for this interview, we're going to be speaking about residential ventilation, and we are not going to be talking in any depth, maybe no more than these words here, about supply-only ventilation, exhaust-only ventilation, or balanced ventilation. We're talking about heat recovery or energy recovery ventilation systems today.
Right.
And we're doing that because we recognize, building science consultants generally, or building science as a field generally, recognizes the fact that ventilation is about health, it's about human well-being indoors, and it is also tied to energy use. Right? If you could passively temper, or meaning preheat or pre-cool the air from outside coming into the building, wouldn't that be great? And in fact, we can.
Right.
Let's talk about residential ERVs and HRVs. So what's the difference between an HRV and an ERV? And I think maybe you should define those acronyms.
Yeah, okay. HRV is heat recovery ventilator. ERV is energy or enthalpy. Most lay people don't know the word enthalpy, so it can be confusing.
Yeah.
So I think in general in the industry, an ERV has been called an energy recovery ventilator. The difference functionally is that a heat recovery ventilator allows you, using only the active mechanical power of 2 fans, to
Which ain't much.
right, to move 2 airstreams, an outdoor airstream and an indoor airstream, and to move those in such a way that those airstreams are exchanged inside the house. So you're basically getting rid of stale indoor air, and you're bringing fresh, quote unquote, fresh outdoor air into the building. And with the heat recovery ventilator, those 2 airstreams are passed through a passive heat exchanger, a core, inside this cabinet where these 2 fans are. And in that core, typically what you'll find in a plate type heat exchanger is many layers with many channels where these 2 airstreams can flow. They're directional so that the 2 airstreams never actually mix or touch, but they're separated by very thin membranes, typically plastic membranes. They could be aluminum or some other material, but usually plastic. And through conduction, the warmer airstream gives off its heat to the cooler airstream. So again, the only active parts of this system are the 2 fans. But yes, that's an HRV. So you can again, with very little energy input, just in a couple of fans, move air and exchange heat so that you can temper. Now you don't have to spend money to either reheat or recool that outdoor air, or at least you can minimize the extent to which you influence the indoor environment. Now with an energy recovery or enthalpy recovery ventilator, we have the same principle, basically the same structure and format of the machine. The difference is in the membrane inside the core, and all those many channels with many membranes now can not only pass sensible heat, but they can pass humidity, vapor.
Oh, you didn't say latent heat. Very well done.
So you can help temper both the sensible, what we feel as temperature, as well as the vapor pressure of the air. And it's similar. The airstream with higher vapor pressure moves humidity to the airstream with lower vapor pressure. Yep.
And so it's interesting, this simple act of changing the incoming temperature, let's just stay with temperature, it could have probably derailed what has been a 10-year delay or so here in Austin, Texas, getting ventilation into buildings generally, and especially homes. And what I mean by that is, about 10 years ago, we were really making great strides with energy code, right? It was 2009, and the whole world was just gaga about reducing operational energy of homes and buildings. And kind of like a casualty left on the side of that situation was health, and was ventilation air. And I can remember really heated arguments with architects and builders about what the heck? We're going to all this trouble to make an airtight building, and then we punch holes in it and bring ventilation air in. That's going to use so much energy. That's just crazy. If you used an ERV in our climate, instead of bringing in, I'll just stay with the heat part, instead of bringing in 100-degree air, you simply temper it. Do this heat exchange that you talked about, and you're getting 78-degree air, 76-degree air. It's depending on what the inside condition is. So that would have quelled a lot of it. But there was also this implicit, any ventilation system that we're going to deem acceptable as an industry can't add cost or complexity.
Right.
And so that was the problem. That's why we ended up with these air cyclers, and they're still used today. It's that I jokingly refer to that's ventilation based on fiction, because you put a 6-inch duct, 15 minutes an hour. You want, let's say, 50 CFM continuously should be 200 CFM for 15 minutes an hour. Right. And hope I didn't just lose you listeners, but basically 15 minutes an hour is a quarter of an hour. If I need 50, I need to multiply that times 4 to get the full hour.
Yeah.
So 50 times 4 is 200. And then you have this 6-inch duct, right? So excuse me, how am I getting 200 CFM through my 6-inch duct, right? And it's twisting and turning. And so tempering ventilation air, this tempering process that you described, it's simply, you've got this dry, cool air mass. Why don't, in humid, and I'm biasing toward hot humid.
Yeah, right.
Why don't I use that dry, cool air mass to temper passively, just using fans, the incoming airstream? And then in a cold climate, you've got some serious cold air outside. There will be a definite comfort issue.
Yeah.
If you don't temper it.
Right. Yeah. And what happens, in the experience that I've had, is I talk to people who, if they have a ventilation system that creates comfort issues, in other words, if that could be, it delivers untempered air or poorly tempered air, or it's just noisy, which can be a function of the machine, or it can be a function of the ductwork.
Right.
But either of those things will cause people to just shut these things down if they're not educated about its purpose and about how vital it is to their well-being. So there's, even if you do go through the effort of doing some of these things and it's done poorly, then people are just shutting them down anyway.
Yeah. Brett Singer talked about that, finding that. Yeah. And unfortunately, when you shut them down, it's not like a red light goes on your body's breathing dashboard saying, you're breathing carbon monoxide now, carbon dioxide, phthalates, plastic, It doesn't happen. So I actually went into continuous versus intermittent, and I want to make a comment on that one. So there's ventilation standards. ASHRAE 62.2 is the appropriate one for for residential. And it's a good basis. There's, this conversation could sprawl out tremendously here. But it's a good basis. And it has this difference between continuous ventilation and intermittent ventilation. And even that is nuanced, because you can do intermittent ventilation with minimal degradation of air quality if you do it right and you do it appropriately. But I think implicit in that statement is, the best way to ventilate is the way you're breathing. It's like you're breathing all the time, let's ventilate all the time. And given that there's technologies to do that, and that relative to the cost of any build, any construction that any of you are associated with, it's relatively minor.
Right.
It just seems sensible to do it. It's really interesting, and this is getting beyond ventilation, but what we prioritize in our buildings are things we can see, things we can touch. Yeah. And air has it rough. Yeah. So continuous versus intermittent, ERVs and HRVs, they're implicitly continuous, right?
No, they're not actually.
Tell me about that.
Yeah, so much of the industry in North America assumes intermittent operation.
Really? Even in residential?
Yeah.
How much intermittent?
It varies, and I think the reason for this is related to kind of the history of the adoption of this technology.
Okay, good.
In North America. The first buildings that were really getting balanced heat recovery ventilation were I think buildings in Canada, residential buildings anyway, and so in a cold climate, and the reality is, even though we're sitting here in Austin having this conversation, the industry basically has its roots in cold climate technology. So in a cold climate, you have to deal with frost, and as you change this air, the two air streams are both changing temperatures.
Yeah.
And relative to the outdoor air in the middle of heating season in a cold climate, the indoor air is relatively humid. And so as it goes through the heat exchanger and it starts to drop temperature, the water vapor in that air condenses. And it's going to freeze. It's because the air temperatures are so different. So you have to have a frost or defrost strategy. And the common defrost strategy is to turn it off,
run a heater,
and either recycle that air through the building. So to not turn it off.
The warm air.
Yeah. But you have variations of that. But basically, in one way or another, you're gonna halt this continuous ventilation process in order to defrost the core.
Mm-hmm.
So, for that reason, again, because that's where the roots of most of this industry are, most designs of products are geared around this intermittent process.
Yeah.
And
interesting.
And the other aspect, I think, is because they're frequently, going back to your comment you made earlier about cost, this needs to be done in a way that impacts costs.
Minimally.
Yeah.
Mm-hmm.
Is that the preferred method is also to tie the ERV or HRV into the air handling system for heating and cooling, and so those typically operate intermittently too. So you just kind of come at it with this whole assumption of intermittence all the way around the conversation.
Interesting.
Is the way it seems.
See, that's my humid climate bias.
Yeah.
I'll put that on me.
Yeah, sure. No.
Because really, from a sensible heat temperature, and just briefly about that, sensible heat really just refers to the fact that the molecules in the air are vibrating.
Yeah.
If they vibrate more with more energy, we call that higher heat. And since I'm talking about that, the latent heat, like if you put a drop of water on the table in front of you, it's going to go away. It's going to evaporate into the air, so that
depending
moisture...
on the relative humidity of the
Right,
air.
you're right. You're right. If it's warm enough and dry enough in the surrounding air mass, that water is going to absorb heat from the surrounding air mass and then change phase and be in the air as a vapor. So now water vapor in the air is absorbed heat or is simply heat. Right, so it's a very simple concept. But so here in Austin, sensible temperature-wise, we've got it pretty easy, right? Like, it goes up to 110 out, which is no slouch. But that's still, if we're keeping it at 70 inside, which is cold when it's 110 out, that's a 40-degree temperature difference. Whereas where you're from, what would be a wintertime temperature difference?
I mean, your average difference in the winter, if you're at freezing, if you're at 32 Fahrenheit, you're looking at a 40-degree difference. We're very often, even in I live in kind of central New England, we very often in single digits during the winter. Not the whole winter, but it gets there quite a bit.
Mm-hmm. And in Canada, it would go negative.
Oh yeah, absolutely. Yeah. So
you could have a 80, 90.
That's right. Yep.
Degree temperature.
That's right.
Yeah.
Yeah. So that delta T really impacts, again, if you're thinking about changing outdoor air with indoor air, it really impacts both, not just the energy consumption, but it impacts comfort too.
Yeah.
Mm-hmm.
And comfort drives behavior. So, how people choose to use the systems will depend on how it feels.
But unfortunately, that's a thermal comfort aspect, right? So they'll feel a cold draft or they'll feel hot air.
Right, that's right.
But they won't feel carbon monoxide.
No, but they respond to what they feel. Mm-hmm. We respond to what we feel.
Yeah. No, not us.
And so, I think this touches on this difference of intermittent versus continuous ventilation. Just like I think we recognize that if we can get a building that can operate in a pretty stable manner, then we avoid a lot of spikes in temperature and a lot of spikes in mechanical activity.
Absolutely.
Then A, we're more comfortable, B, we're more energy efficient. And that works, and it doesn't, so it sort of drives acceptance. And people are cool with those systems that work that way. If you have a system that's operating intermittently and you're in an environment where your delta T could be 70, 80, 90 degrees, and you have marginal heat recovery effectiveness in your appliance, that's you're going to feel that
you're
in the
gonna be
building.
uncomfortable, yeah.
And you're not going to want to run it if you don't have to. So you'll look for ways to shut it down. You'll look for ways to use it minimally. Whereas if you can have a system and a quality of appliance that allows for continuous, comfortable operation that deals with that delta T, then your rate of adoption is much higher.
And that's, I understand your logic now. That's why in the North American market, HRVs were how this system got introduced, right?
HRVs were kind of the first wave of technology. We just thought about that thermal difference. But the other thing about HRVs is, well, because this whole industry, I think, really got its legs in the cold climates. You think about intermittent usage. One of the things that you're dealing with indoors in a cold climate during the heating season, especially if you're ventilating, you're changing the relative humidity. As soon as you bring that outdoor air in, which is already at a very low RH, you bring it indoors and you heat it up. Well, you drop the RH even more.
Yeah.
So maybe we don't have to explain all that in this conversation, but it's just the fact. So ventilation in a heating climate tends to dry out a building. When you're using ventilation intermittently, that drying effect is sort of mitigated.
Yeah.
So when you're using intermittent ventilation, an HRV is less detrimental to indoor comfort during heating season in a cold climate. Once you start ventilating continuously with an HRV in a cold climate, you feel that dryness kicks in fast.
So how do you deal with over drying during winter?
Using an ERV is a better choice in almost all heating climates if you're going to do continuous ventilation. You drop a little bit on your sensible recovery. The membrane structure and material is not quite as effective at transferring sensible heat, but the payback and the latent is terrific. So again, in a heating climate, what that means is comfort. In a cooling climate, an ERV is absolutely essential. You know.
Yeah.
Because it allows you to reject outdoor humidity as long as you are conditioning the indoors.
Right.
You use, you spend energy on cooling and drying the indoor climate, and now you can use that cool, dry air mass to your advantage in an ERV, because as you send that through the core, it will suck heat across the membrane from the outdoor air that's coming in. It's funny how these questions and thoughts are intertwined so much. Intermittent use, HRV use versus ERV use, and kind of the origins of our industry. They all sort of, it's a puzzle that fits together in a way.
Yeah, well said. We actually had a project, I guess about a year ago now, it wrapped up in Seattle, and got down to the, quote, simple choice of HRV or ERV, and had some challenges.
Yes.
It's a very intelligent project team, the owner completely committed to health and well-being. That was one of the main points, and of course energy efficiency. And we were advocating for an ERV, and what was commonly done was HRVs, and it was pretty simple, but basically we picked a couple of times a year, showing them that in their climate for certain times a year it was very humid out for 3, 4, 5 days in a row, and if you had an HRV then you'd be running your dehumidifier that much more. So it was a fairly simple argument that actually had a lot of people going, oh, really? The general contractor who had this project plus 10 other projects with HRVs now is going, oh, wait, if this one's going to go with an ERV.
Yeah. And the Pacific Northwest is a strange area because I think it's a heating dominated climate.
It's not too humid too often.
I've got a colleague on our staff who is in, I always mess it up, but he's basically right outside Seattle.
Okay.
And he says they've got a couple of different climate zones right there.
Huh.
And choice between HRV and ERV really comes down to whether you're in that marine climate or you're just off of that, and it can be the effect can be dramatic. So that's an area, and then there's I've got another colleague in our company who's based in California. And California is a place where there's like 16 different climate zones or microclimate zones or however you say it, right in that one state. You know, that those choices can get difficult, but for most of us around the country, the choices are pretty clear. In the Northeast, with the caveat that we're typically talking about continuous ventilation, we call for ERVs almost all the time. And the only time there that we wouldn't is when the occupancy is going to be high for the space. So if you're in a multifamily building that maybe it's a low mod housing project, and you know, for the square footage you're going
What's that mean, low mod?
Low to moderate income. So it's typically a subsidized housing project with public funding, and the design footprints of the apartments are smaller. Occupancy is usually a little bit higher than average. In those settings, our logic of using an ERV to maintain some comfortable indoor humidity during the heating season kind of goes out the window, because it's a smaller space, there's more people in there, and the moisture that gets generated in those buildings is much higher, so you're looking to evacuate that moisture, you use the HRV. So there's a few caveats, but by and large, for a lot of the country now, even in Canada, if we're talking about continuous ventilation, we're thinking ERVs almost all the time.
So hot, dry might be a place where an HRV.
Yeah, right. That's right.
HRVs. Let's talk a tiny bit more about HRVs and ERVs entering the U.S. market. I don't want to make this a quiz or anything, but where are we in that? I mean, do we know what percentage of new builds get an HRV or an ERV?
Well, it totally depends on where you're at in the country.
Well, where you are in the Northeast I would consider fairly advanced.
Yeah, that's interesting.
Well, down here, very, very few.
Sure.
We're putting them in our designs.
Yeah, and I'd say it's very few up north as well. So the code is starting to drive it a bit more, but code officials are people that, just like the rest of us, that need to come up to speed. They're people that
Code officials are people.
They're trying to learn things. I'd say in the Northeast, adoption is still fairly slow. There are places in the U.S. I see, like the state of Minnesota, I think has a code now that is pretty much requires an HRV or ERV in every new build residentially. There might be other pockets in the upper Midwest that are like that. And certainly Canada, there's a lot of provinces in Canada where HRVs or ERVs are mandated.
Those Canadians.
Yeah, but
on their game.
But I'd say it's still a pretty slowly building product category throughout the rest of the country.
Yeah, and this gets back into lots of social science and social psychology and the change of markets. Like, why? Like, the rest of our world is technologically sophisticated, but homes and residential buildings are less.
Yeah, and there's cultural stuff that I think this gets real anecdotal and whatever, and it could get mean, I suppose, but but I feel like in our culture, when we talk about health and wellness, we there's a lot of superficiality that kind of still
healthcare
drives the way that people think about that.
Care.
Yeah, exactly. So what does the healthcare system look like? How do people think about health? And then how do we perceive people that are well? A lot of that can be driven by aesthetics. So the point that you began with, which is that we don't see, smell, taste most of the indoor air quality issues that affect our health and well-being. We're unaware of. Out of sight, out of mind.
Yeah,
so,
you could almost argue, Chris, that it's not even psychological. It's like mammalian, because we're mammals, right? If we had evolved to sense PM 2.5, and if we had evolved to sense carbon monoxide, but there was no need to. So we didn't, and then in a relative recent past, we moved to this place called indoors.
Right. Yep. There's and I wish I have told people I work with, I wish that we had produced this video. Maybe you guys have seen it, that from VLEX Skylights put this video together.
Oh yeah, the chamber.
Yeah.
Oh, incredible.
The indoor generation. And a terrific presentation.
Yeah, we'll link to that.
Yeah. And to VLEX's credit, you know, they didn't push skylights a whole lot in that video that they made. They just really called public attention to this issue. We take indoors for granted. You know what it means for us. We don't think about.
Yeah.
And
we live in a fishbowl of
yeah.
our own making, and we don't currently clean the water.
Right.
And we are pooping in it in some ways.
Yeah, and you know,
in it.
geopolitical issues and climate issues and resource issues, all those things have kind of converged in recent decades to say, well, we need to make our houses tighter. We need to insulate them better and control, you know, don't make them less leaky. And that's not a bad thing.
For energy, for operational energy.
Yeah, right. And even for our health, as long as we can control the air quality and airflow in and out. Mm-hmm. I liken it to human biology. You know, if when a baby comes out of the mother's womb, that first thing everybody's looking for is for them to open their mouth and to take their first breath. And it's a cool thing, and yet it indicates that there's a very controlled way that we breathe, and that those passageways have very distinct purposes. Their structures and makeup and everything are completely geared to the function. You wouldn't take a baby out.
This is from a man who has 6 kids.
Yeah, right. I
got to watch this.
I'm staying here in Austin with my oldest son who lives here, and I caught him from the womb. Yeah,
and he started breathing.
He did. But you wouldn't take a baby out and just randomly start puncturing its chest with an ice pick in order to say, oh, it needs to breathe. It needs to breathe. No, there's a controlled way that we breathe. It's by design.
You're talking about a building with
why, you know, the idea that we expect buildings to breathe through random leaks.
Yeah.
Meanwhile, we're systematically developing our industry to eliminate those leaks. We have to have a more controlled, deliberate way of.
We here have been talking about the air distribution systems generally as being the lungs of the building.
Yep.
And in fact, this one is you know, ERVs and HRVs are truly the lungs of the building. I mean, this is the breathing end of it, because the other lungs of the building are delivering temperature change for comfort. But this is. Let's talk about cores a little bit now.
Yeah.
We talked about enthalpy and heat exchange cores. And you said it was made of plastic, but it's a thin plastic, right? So when you think plastic, it's not like it's just a plastic wall. So it's this interesting plastic where the heat can flow right through it and the moisture can flow right through it, but the air masses stay separate. Let's see. How did cores come to exist? Do you know? Like, who did the initial research? Enthalpy recovery cores or energy recovery cores? Yeah. Like, where did those come from? Like Tyvek? Someone just said, "Hey, look, a piece of Tyvek works like a."
Well, it's interesting. We have a man who's a consultant for us now, but actually founded the Comfort Systems, which is it's a brand name. But Dr. Rudy Creasy is a really interesting person who was trained as a mechanical engineer. In the 1980s, he traveled all around the U.S., and he was particularly interested in learning about the energy conservation practices of the developing U.S. market.
Yeah.
So in the 80s...
We were on our game.
Yeah, we were. Yeah, we kind of were taking the lead. Mm-hmm. And the Europeans were coming here to learn from us.
Wah, wah, wah.
He went back, and eventually, the thing that's important, I guess, to my reference point with Rudy Creasy is that he went back. He ended up developing an entire building standard geared primarily around energy conservation. It did include some technological or renewables like solar, thermal, photovoltaic, but really he built a subdivision and did it as a study and monitored everything. They produced everything they needed for the entire year with the sun and with a cord or two of wood. And that was all their heating
In
and
Switzerland.
domestic hot water in Switzerland.
It's pretty darn cold.
Yeah, but he came here to learn about it. So I think a lot of core technology was developed here in North America as well, and the whole heat recovery ventilator technology was.
So let's make it more real. So we have a bunch of ERV manufacturers around the world, and they buy material to use in their cores.
Mm-hmm.
Where do they buy it generally? And someone's making this material.
Yeah.
It's like a shopping center for ERV cores.
I think there's a lot of vertical integration of supply chain that's occurred, and then there's some split offs and some competition, and this is typical industry stuff. But
so there's a handful of manufacturers of core material.
Yeah, probably.
Mm-hmm.
So our technology that we use at my company has all been purchased, so it's become vertically integrated.
So someone was making core material, and your company purchased that someone.
Yeah.
Interesting.
Yeah.
And then so now you sell core material to other manufacturers?
That's true.
Ooh.
Yeah, and cores.
And cores.
Yeah.
Oh, the whole core, not just the material.
Yeah.
Wow, fascinating.
And the development. So early on, I think metal was used in these cores. So the membrane was metal. And, you think, well, it's conductive. That's a good...
It's going to move heat, definitely. Yeah. Not much moisture is going to go.
The effectiveness, and you can't really just talk about membranes or the plates inside these heat exchangers without talking about the stack up of the whole heat exchanger itself, and ultimately what kind of effectiveness you get in the heat exchange and in the enthalpy exchange.
What do you mean by that, the stack up?
Well, in other words, so you ultimately it's the system that performs. You can kind of look at a membrane or a plate within a core and say, okay, well, this membrane, here's the performance of that membrane. But you don't apply a membrane to a house; you apply a system to a house. Mm-hmm. And so the core is the heart of that system. It's the you can talk about tissue in each of the air sacs in your lungs,
right?
But apart from assembling that into a fully functioning lung with a diaphragm
and a human body,
right. It kind of doesn't matter, and you can extend that
holes
to
that you want to pull the air,
right? Your nasal passages, etc. So all that matters, and it has to be thought of together. Anyway, as you stack it up, and this is what happens with the membranes, practically speaking, is these membranes or plates get stacked up to form a core. So again, you have many layers of channels that opposing airstreams are passing by each other in. As you stack that up, you create a certain amount of surface area. Same exact thing with your lungs.
Mm-hmm.
I learned in high school or college that if you took the average human being's air sacs inside their lungs and you laid them out flat, it would cover a tennis court.
Yeah.
So
it's actually more like half of a tennis court.
Okay.
But it's on the order of,
but huge huge surface area.
That's your alveoli.
Yeah.
Wow.
And that's the similar type of scale that you've got going on inside an HRV or ERV core. Okay. There's a lot of surface area that you're working with. So so when I say it's stacked up, that's literally what I mean, and you're creating a lot of surface area. And you're running a certain amount of air through this core
at a certain speed.
Yeah, right.
Residence time.
So you get into talking about rates. Mm-hmm. How much air is passing across how much surface area in what period of time? That has a lot to do with how effective this core is at transferring heat and humidity.
Which will then impact the size of the device.
Exactly.
Like the size of the fan.
Yep. And so in a market, and I'll just make this real again, in a market where this isn't a widely accepted product category, and the people who are considering it are almost always considering it as an afterthought, are looking to, all right, can we shoehorn this into a ceiling in a closet somewhere? Where does this go? We haven't previously envisioned a space for this. So the pressure is on to minimize the size of this thing.
Yeah. Which means to make the core badass.
Yeah.
Functional.
Yeah, but the reality is, and this gets back to the materials, you had to ask me originally about materials. Once you get down to the level where you're stacking that many layers together and you're trying to compress all this, the conductive advantage of metal versus plastic begins to lose ground. And so there's a couple of factors. One is that you have an air film on every surface, so you're pushing air through these channels, but there's an air film next to the membrane itself that really isn't moving very much.
Right.
Once you get to these thin layers, the air film ends up having, more impact on the conductive quality of the membrane than the membrane material itself does. So now you get into a manufacturing question. What's easier to manufacture? And the plastic membrane, once it gets that thin, it's easier to manufacture the plastic membrane with the channels, create ripples like a Lay's potato chip that has lots of surface area on it. And so plastic just becomes the favorite.
Fascinating. I hadn't thought of it from a manufacturing standpoint. Are there still metal core ERVs?
There probably are. Every now and then I see something maybe at a trade show or
maybe more commercial. Even
in the residential realm. So again, this in an immature market, cost is a huge driver. So there's the pressures on throughout the industry to sell things cheaply, and so you got to make them cheaply.
Yeah.
And so there's people that use old technology that they can acquire cheaply. There's all kinds of things like that impact the design of some of these machines.
Mm-hmm. Okay, but you made a really logical segue into talking about the systems.
So once you transition to a material that you want to be able to move moisture across as well as sensible heat, then you need a different material. And where exactly that first ERV membrane material came from, I can't say. I know that in our company, the material that we used, the man that first developed this membrane wasn't in the ventilation business. He was in some other manufacturing process business where you were interested in moving moisture, and so that's how that got developed. And then he discovered the application of this material. He realized, I don't know how he came across the information, but he realized that it was actually formed better than any other ERV membrane material currently on the market. And so he made his pitch and started building ERV cores.
Is that where Zehnder came from?
No, it's not where Zehnder came from, but Zehnder
bought that company.
Zehnder started buying the membranes from that company and using them in their facility to build up their cores, and then eventually acquired the company that was developing the membranes and kind of merged those two branches together to form one company.
All right.
And so, core is
That's
the name of the company. Yep, and it's an acronym for something which I can't recall.
Oh, really?
But Core is the new company as of a year or two. It's probably 2 years ago now, and it was a merger of D Point in Canada, in Vancouver, and Powell in Germany. And Zehnder had acquired both of those companies, been operating them for a while, and then combined them to form this team. Core.
That's fascinating.
And so Core is now selling products to a lot of manufacturers in the industry.
And I could see, we're not going to go down this road, but I could see that if Miguel, you're Core and you're developing a range of technologies, but you're owned by one manufacturer, you're not going to sell your best ones to your competition. It seems like I'm going to keep the best technology.
Right.
All right, so you have this core, enthalpy heat exchange core. And, let's just, real quick, so enthalpy is heat. If you had no moisture, enthalpy is just sensible heat, right? So enthalpy, but, I'm a physicist, so I think, why would we use another word? Enthalpy is so perfectly appropriate for this.
It's sufficient.
Yeah, it's sufficient. Yeah, necessary and sufficient. So you have this core, and now you need to bring air in from outside, pass it through the core and send it to the inside, and you need to bring air out from inside, pass it through the core and send it outside. Fans move those air streams. Where is the industry at with fans right now? What kind of fans are being used?
Most manufacturers who are trying to advance their business are moving to ECM motors, electrically commutated motors, or electronically commutated motors, and they're basically they're both very efficient in their operation, low watt draw, and they're highly controllable.
I can't imagine anyone's using PSC motors, permanent split capacitor motors.
Yeah, I'm not a
commercial
mechanical designer, so I guess I don't know much about that. But
yeah, it's not that. So now you have the fans, you have this heat exchange core. I know that there's a difference between cross flow and counter flow.
Yep. That's right.
Most cores, as I would understand, have some combination of both cross and counter flow today.
I think so. cross flow was pretty much the standard for a long time.
Like air moving at 90-degree angles. to
Yeah,
each
if you
other.
if you do a internet search of HRV and you look at the images, you almost always see this square tilted at 45 degrees, so it looks like a diamond shape.
We'll put a picture of this in the show.
Yeah, and that's there's and basically that functionally that's what you have. You have 4 faces to this core. 2 opposite faces are for the outdoor airstream. So it's entering on one side, it's passing through the core and exiting on the other. So on the first side, it's technically called outdoor air. After it passes through the core and it's exiting the core, it's now called supply air.
Supply.
As it's heading into the house to ventilate the house.
Supplying the house. So outdoor air becomes supply air.
In the other direction, crossways flow through that core. You have extract air. We typically call it exhaust because we just kind of lump that together. But it's more accurate to call it extract air. Some people call it return air. But it's air that's being extracted from the house.
And from specific locations, ideally, but we'll get
That's right, yeah. And it's passing through the core, and after it passes through the core, then we technically call it exhaust air because it's going to be directed outside the house through exhaust duct.
Okay.
So
outdoor air, supply air, extract air
becomes
and exhaust air. And I confess I call it return air, ERV return.
Yeah, and I do a lot of times too. That typical picture that you see of that diamond-shaped or square-shaped, kind of tilted on its axis core, has got those 2 cross-flow airstreams. And this is oversimplifying it a bit, but if you drew 2 vectors that represented those airstreams, they would intersect at one point. Now, the reality is that inside that core, you've got all these multiple, hundreds or maybe even thousands of little channels that have been formed. So as they pass by each other, they're passing by each other at many little points. But if you just take 2 channels, they're passing by each other at one point of intersection.
So that's cross flow.
That's cross flow. And so you have at that...
That's like an intersection in a road.
Yeah. And you have at that one point is where your heat exchange or enthalpy exchange is going to take place. It's more sophisticated than that because, again, there's multiple channels. But if you break it down, each channel is...
You had a single core ERV.
Yeah.
I'm sorry, a single... what would that be called? Like a single tube in the core?
Yeah, I'd call it a channel or whatever.
Single channel, there you go. Thank you, ERV.
Now, that's cross flow. If you talk about a counterflow heat exchanger, it's a little different. A giveaway that you're talking about a counterflow heat exchanger is that the core is not square, it's hexagonal. You've got 2 outer edges that serve the same function, which is they're going to be the place where air enters and exits in each direction. But you've got this sort of rectangular section in the middle. If you chop off one triangle from one side and the other from the other, you're left with this rectangular section.
Makes sense.
And what happens in a counterflow heat exchanger is that the air enters into those angled portions, but then gets directed so that it comes straight across the rectangular portion in the middle. And now you have 2 air streams that come at each other directly opposing. And as I do in a lunch and learn, I'm always holding my hands up with my fingers pointing at each other. But
it's like a 2-lane highway.
Yeah, exactly. Yeah. So if you just break it down to 2 lanes, like we talked about in the last one,
2 channels.
Yep. Then they're passing by each other. Yeah, like a 2-lane road with a center dividing line, and they're passing by each other for a good long distance. So you have all that much more time for heat and enthalpy to exchange between the airstreams, and you multiply it over hundreds or thousands of channels, and you can get to a much more effective exchange of heat and enthalpy.
Another quick pop quiz moment. You just mentioned hundreds or thousands of channels. Do you have any idea? Is it hundreds?
Oh, easily hundreds, yeah. And
it's not thousands. I don't know.
Oh, it could be in some.
Wow.
No, probably not. You're probably right. It's probably hundreds.
I don't know.
It's probably hundreds. But again, it goes. So if we, and I don't want to get ahead of where you're going with the question, but
please go wherever you want.
But if you take that to the next level, we've said it already that the more layers, the more channels that you can devote to this, and the more layers that you can devote to this. Let's say you're talking about a system that's going to run 100 CFM. Well, if you give a small core to this process that could fit inside of an 18-inch square box, and you say, well, that's gonna be what however much surface area you can get out of that, or an 18-inch cubic box. Well, that's how much surface area you create. if you expand that and you say your core is roughly 24 by 24 by 24 inches, well, you've just picked up a lot more channels with a lot more surface area. If you run that same 100 CFM through that larger core, your sensible or enthalpy recovery effectiveness is going to be much higher.
Mm-hmm.
Core geometry and size impacts the performance of these systems.
I get it. I hadn't been thinking about the layers so effectively. So it's corrugated tubes, corrugated channels, very much like cross-section of cardboard.
Yeah, I'll give
and multiple
exactly.
layers
That's
of
right.
cardboard.
Yeah.
Let's go ahead and go to effectiveness now, and then we can talk about ductwork or distribution. First, we need to define terms. Well, go for it. Define terms for sensible and blatant.
When we talk about recovery effectiveness, what we're talking about is measuring and being able to state how effective this system is at extracting heat from the warmer airstream and transferring that to the cooler airstream.
Right.
So we talk about...
so it's like a grade on a test. You can get 100%.
Yeah. And the percentage, when we talk about, let's just for starters talk about SRE, sensible recovery effectiveness, graded as a percentage. The percentage is referencing the delta T. So if your outdoor air, let's say we're in a cooling climate, your outdoor air is 92 degrees and your indoor air is 72 degrees, you have a 20 degree delta T Fahrenheit. If you have a 90% sensible recovery effectiveness, then you're talking about being able, using this system, to recover 90% of the heat from the outdoor airstream and transfer that to the indoor. 90% of the delta of the temperature difference.
That's amazing. Does it translate down to 18 degrees? 90% of 20?
Exactly. So if that's our example and we have a 20 degree delta T and we have a 90% sensible recovery effectiveness, then we're going to be moving 18 degrees. And so now, let's say we start out with a 92 degree outdoor air temperature. It goes through the core. It goes from being outdoor air to becoming supply air, and as supply air with the 90% effective recovery, it now becomes 92 minus 18, so it's going to be 74 degrees.
You can see why I said it would have quelled that initial fervor here. Like, no, you can't bring all this ventilation here. It's like, no, what if it's 74 degrees?
Yeah.
But now, can these things be 90% effective?
Let's talk about that in a minute.
Okay, go. Lead me to it.
Yeah, and the flip side, so where does that 18 degrees go? Well, it attaches itself to the extract air and becomes part of the exhaust airstream.
Yeah.
So your extract air went from 72 degrees, picked up 18 degrees, and got extracted as 90 degrees. With an ERV, you have not only the heat transferring, but you also have humidity transferring. So typically, I'll state numbers that I'm familiar with our products, and I think it's a fairly decent representation, probably, of a decent enthalpy recovery membrane. We talk about in terms of roughly 2/3 of the delta in humidity, and we're talking about absolute humidity.
So grains.
Yeah, you got to break out your psychrometric chart in order to really get at what that feels like and what it's going to mean. And
so you would use dew point or grains for that.
I mean,
people usually use
the applications that we look at are usually just going to break it down and do the math for you, and it's going to turn into RH. It's a discussion about it gets represented as RH because that's what's meaningful to people usually, at least to lay people.
Which is another shame, but
yeah,
we'll hang our hat.
And I'll confess that I'm not a physicist or a mechanical engineer, so I'm shifting in my own brain about how to think about dew point. So you asked about where's the industry at in terms of effectiveness? Well, I said earlier that the membrane material and configuration that makes enthalpy exchange possible, that allows you to pass humidity, means a bit of a compromise on the sensible recovery. So, whereas a really good SRE in an HRV that's only dealing with sensible is the 90% range. Woohoo! Caveat: this changes with fan speed.
Of course.
Because
and entering conditions
how much
and leaving conditions.
Sure, but how much air are you pushing through this in a minute? If you're pushing a lot of air through it in a minute, all these numbers drop. These recovery rates drop because you're not giving it the same amount of time to exchange energy.
Well, this gets back to the intermittent versus continuous. If you did it continuously,
That's right.
you could have lower flow
That's
rates.
right, exactly. Lower flow rates, overall, it's more effective. If it's more effective, it's more comfortable. So, yeah, there's...
All right, so you get back to my point that why not do continuous?
Yeah.
I mean, especially if you don't have to worry about defrost, which
I'm with you.
talking about.
I'm with you. So typically, where the industry is at is this. So again, because our industry is dominated by cold climate mentality, and there's all this bias towards intermittent usage, kind of governing body that rates these things and lists them in our industry in North America. They sort of set a mark right around 60% for sensible recovery effectiveness for an HRV or ERV. So basically, for instance, if you 60% would be a minimum standard to meet if you're going to be listed with Energy Star Canada, which increasingly looks like it's going to be, if you want to sell a product in Canada, you're going to have that listing. So 60% recovery effectiveness, SRE, is it's kind of a low threshold. That's not in the industry today. That's not that difficult. Better machines are like the standard is probably somewhere in the maybe 70-75%. A good machine should be getting 90% as an HRV. As soon as you jump to an ERV, you give up a certain chunk of that sensible recovery effectiveness.
Yeah, but you benefit.
But
we talked about that.
Yeah, right, exactly. But to put the numbers out there, a good HRV core that would be at 90% plus is probably going to be in the low to mid 80s as an ERV in terms of its SRE, its sensible recovery. And the latent will be about 2/3.
So low to mid 80s, let's go back to that 20 degree, let's say mid 80s, 85.
Yeah.
That 20 degree delta T.
Yep, you're talking about 17 degrees.
Yeah, 17 instead of 18.
You're recovering 17 degrees.
So let's not say low to mid 80s, we just get a B in
Yeah, no, that's still excellent. Yeah.
Yeah.
I mean that's very impactful.
What about LRE? Latent recovery effectiveness.
Yeah, so LRE actually only applies to ERVs, right?
Makes
So
sense.
in HRV, your LRE is going to be 0 because you can't recover any moisture. But again, this is going to depend on kind of the core material. It has an impact on that. It's going to depend on its application to the core, how's the core built, and then how much air you're trying to drive through it. But in general, if you think about in normal operating speeds, a decent ERV core ought to be able to transfer somewhere around 60 to 70% of the difference in absolute humidity.
And that's a profound difference in a humid climate for the indoor microbiome and all the associated benefits of keeping your home interior dry. It's just profound, and it just. Okay, this is me being anecdotal and speaking as a person. It just boggles my mind that it's still so hard to get ERVs accepted into our industry. And 10 years ago, it boggled my mind that dehumidification was an uphill fight, which is now not so much. And then one quick caveat there is, in a humid climate, the ERV LRE, the latent recovery effectiveness, it is dependent on having this dry air mass. The dry air mass potentially from the dehumidifier, or it could have been from the cooling system.
Yeah.
The dry air mass is in fact the motive force which does the enthalpy tempering of the incoming ventilation air. So that's one thing, and I'll say it again because a lot of you listening don't seem to understand this simple point. ERVs do not dry the incoming air unless the interior air is dry to begin with.
Another way of saying that is, we talked about an LRE, let's say it's 65%, that's great. 65% of what? 65% of the delta in humidity.
That's a great way to say
So if the indoor humidity has risen to a point where there's very little difference between indoors and outdoors, the ERV can't work against that.
Yeah. We have 70 degree dew points outdoors commonly. I mean, low to mid, very, very commonly. And I definitely measure upper 60s in a lot of homes where humidity is not controlled well. You want it in the low to mid 50s in dew point interior. So if you have 68 degree dew point inside and 72 degree dew point outside, and you have 75% effectiveness of 4 degrees of dew point, now I have 3 degrees dew point difference, so I take my 72 down to 69. And that's a better way to say it, in fact.
So if you're conceiving of a mechanical system for a building that is going to have ventilation, and it's going to
you mean it's going to have people in it?
It's going to have people in it.
So it has ventilation.
So there's going to be mechanical ventilation, and it's going to be conditioned. So we're going to make it comfortable, and we're going to make it livable, healthy. If you can conceive of these systems working together, they help each other. So a good ERV lessens the load that an active dehumidifier has to do or address.
Absolutely right.
And
given that you're ventilating.
Yep, given that you're ventilating, because the ventilation air, and this has to be acknowledged, that in a climate like Texas, your ventilation air is going to be your biggest source of latent load inside that house.
Mm-hmm. Absolutely. Refer to Lou Harriman's work, ASHRAE Guide to Humid Climates.
So a good ERV is going to make a dehumidifier have to work less, and a good dehumidifier is going to also make the ERV more effective at doing passive latent transfer. So,
right. Yeah, it's fascinating. So I'm getting a little signal from Miguel. We're going to be wrapping this part 1 up, and we're going to keep going because there's definitely more topics here. But for those of you listening, this is the end of part 1. And who knew that the V in HVAC could go so deep and so wide? I mean, there's so much to talk about.
Who knew the V existed?
Yeah. HVAC without the V. Thank you very much.
You're welcome. Thank you.